Let me introduce myself, Andrew Scott. I'm from Beaverton, Oregon, which is the headquarters of Tektronix. So I'm a product line application engineer responsible for a couple of products, one of which is Cerify, our file-based QC product. So I'm going to talk not so much about the product itself, but about file-based QC in general. And I'm actually going to start by talking even further back about what a file-based workflow is like. And I'm going to go into a bit of detail on one specific file format. I'm going to talk in detail about MXF, which is a relatively new format in the big scheme of things, I guess, but it's designed around professional video applications. And so it was designed for our industry, unlike some of the other file formats being used. And then the last part of the presentation is where I'll talk about QC in general. So it's not so much a product pitch about Cerify, though my screenshots will be of Cerify, but just about what we mean by quality control in general. So over the course of the next hour, I've got some content at the 50,000 foot level and some at the detailed level, so there's something for everybody. So we'll start off by talking about a file-based workflow, and I guess this is the 50,000 foot part. I've got a diagram I put together of sort of the key components of what we mean by a file-based workflow. And you know, as I go around and visit our customers, I see that everybody's doing something slightly differently, but some of the key parts of the architecture are similar. On the left-hand side is where we will ingest into the system, and this might be, you know, a direct recording, might be a recorder like we saw with the Cinedec product, might be you know, recorded off a satellite, or a file transfer. You know, it gets into our system at an ingest server. Here I'm showing a centralized storage system, the nearline storage. Nearline is a contraction of near online. And really what we mean there is it's a high-speed shared storage system that's accessible by different parts of the workflow. So from here we can go to playout, from here we can go to archive, a different storage system with different characteristics. We've got editing, we've got transcoding, and our quality assurance, or our QC system, are all basically attached to this common centralized nearline storage. And then on the right side of my diagram, I've got our various types of playout. So from traditional broadcast playout to some of the new mediums in which content is now being repurposed and delivered in a variety of other formats. And really, I think the transition to file-based video has enabled a lot of this. I mean, obviously there's a lot of other enablers, the rise of, you know, tablets and smartphones and things like that, but still it's a different files, different codec types are often used for this kind of delivery versus traditional broadcast. So let's look at some of these elements in a little bit more detail. First, on the ingest side. So here I'm showing, you know, we've basically got camera input, maybe it's tape ingest, we have a conversion from tape to file, maybe a satellite delivery, could just be a file transfer, basically getting something into our system. At this point, we may have an opportunity for doing QC with a, you know, on the baseband signal, so a serial digital signal, and that's where a traditional product like a waveform monitor can look at that version of the signal. Once it's in the file-based domain, though, you know, to look at it on a waveform monitor, you've got to play it out again. So that's where other tools come into play in terms of looking at the content once it's encoded into a file. Part of that ingest process, creating the file, what we're doing is combining together the video, the audio, and metadata. And I'll explain in more detail what I mean by metadata. The next part of the workflow cycle, here's where I've got my nearline storage, and I've got editing and transcoding, my QA system. One thing in all my diagrams, you see I've got up in the corner a media asset management icon with lines sort of, you know, pointing to everything. The idea here is that the entire system is under control by that asset management system. That's in charge of directing the files from, you know, from ingest to transcode, sending it to the QC system, getting the results, and making a decision based upon whether that file passed or failed. So the asset management system, or the MAM, is pervasive in all these workflows. Some smaller workflows might not have need for a full-blown asset management system, and there we typically automate things through the use of watch folders and move files along sort of semi-automatically that way. But in larger workflows, almost always you'll see a media asset management system in control of everything. As part of this process, you see I've also got a transcoding system. The transcoding here is shown as a separate element from our storage. These are often, farms of other servers that are devoted to that singular task of converting from one format to another. So transcoding is basically changing it from, format A to format B. Might be a different codec type, a different container type, maybe just a different bit rate of the same file type. We transcode because we are typically working with the file in a different format than what it's eventually played out at. Again, the media asset management is pervasive here, basically as hooks to all of these different elements. The distinction between nearline storage and archive storage, nearline is typically high speed, so fast access, multi-access. There's a lot of parts of the system that are hanging off of this, so it needs to support a lot of concurrent playout to your file transfer, to editing, to playout, to QC, and so on. And this is typically much higher storage capacity, petabytes of capacity in some cases, where we've got months or years of programming saved. Archive storage is not immediately connected to the playout system, and we've got to bring content from archive back to the nearline storage if we're going to be working on it. And that's part of the job of, again, our asset management system, moving content to and from the archive system. Archive storage formats are often different from the mezzanine formats or the playout formats. So there might be the need to transcode something into an archive format. It's not always the case, but that can happen. And then moving to something to archive is another opportunity for us to QC it, especially if we do transcode it to an archive format. We might want to check to make sure that it's all intact before it gets saved there and sort of forgotten until a few months down the road until it's needed again. So on the playout side, I sort of mentioned from the nearline storage is usually a cached version of the next however many hours of content it's ready for playout. The automation involved here, this is usually where you're constructing your program list and where the add insertion spots are and things like that. This side of the playout server is where we can look at the signal yet again in the uncompressed domain, so with an SDI waveform monitor, or perhaps we can look at an MPEG transport stream if it's terrestrial broadcast and that sort of thing. So there's other monitoring tools once we convert back from the file domain to baseband or a transmission format at that point. And then lastly, I introduced the idea of content being repurposed for other applications. And I think, again, the notion of different codec types, different container types, file-based workflow has enabled a lot of that, right? The screen resolution, the available bit rate, and so on for a mobile device may be quite different, obviously, than terrestrial broadcast. Different codecs, different file formats enable delivery to those kind of devices. So more and more we're seeing content being repurposed multiple times and made available for different delivery methods. What that means is typically a lot of transcoding. So a specific example, I visited Amazon, and of course they have content available for download, for purchase, and so on, or for rental. They have up to 17 different formats for some of their programs, depending on what the end device, the end application is. So to take that original program, we're transcoding it to all these different formats. That also means there's a possibility of something going wrong 17 times. And the proliferation of those formats means that we want to do a QA check potentially at that stage as well, post-transcode. Okay, I'll just spend a few moments talking about the storage systems themselves. And really in in the video world with a file-based workflow, we're borrowing a lot of technologies from the IT world. So, there are some relatively unique demands with respect to video files. For example, many of them tend to be quite big, right? We don't have to necessarily manage lots and lots of small files, but lots and lots of big files. In terms of the access speed, we obviously need to play back multiple streams of video at play rates without any stuttering or buffering involved. But still, underneath all of that is traditional IT technologies that are just being repurposed for the video world. So for example, we can have storage area networks, network attached storage. So these are servers that are dedicated for storing our files, the nearline storage systems, with standard interfaces. So storage area network might use something like Fiber Channel. Often we'll see just plain servers with multiple gigabit Ethernet links going through common network switches. So from Cisco, Juniper, companies like that. Some of the protocols here. So for file transfer protocols, we've got Microsoft protocols, FTP, NFS, so on. They're standard industry protocols for files. The difference now is you'll see new vendors popping up for video servers that are sort of optimized around the video application. What I mean by that is contrast a transaction server which may deal with thousands and thousands of small files. Video files are kind of large, right? And so we need a storage system that's optimized around storing and serving lots of large files and having multiple concurrent playout. We can't really withstand a lot of interruption on that playout, right? We want, especially on a playout server, you want the video to not have any hiccups because of other network traffic. One example I can think of that, one of our customers was experiencing weird dropouts in their MPEG transport stream for some of the really late night programming. It turned out that the same network that they had their, from their nearline to the playout server, there was doing a 2 a.m. database backup, and that increased network demand from a database transaction was causing hiccups on the playout. So what that means, I guess, is there's some IT engineering involved, some network management. Some of those skills are now necessary in the video domain for a file-based workflow. So that's on the software side. On the hardware side, again, we've got the need for high availability with a video system, and that's where, again, industry standard technologies like RAID come into play. So RAID stands for the redundant array of independent disks, I believe, but the idea is you have multiple physical hard disks that work together to present one file system. And the idea is if one of your disks dies, the information is stored redundantly, scattered across the multiple disks. You pull out the one that fails, you haven't lost any information. When you insert a clean, blank new disk into the array, it rebuilds that redundant information, and you still got your file intact. So again, it's a technology that was developed long before video file-based workflows, but now repurposing that in the video servers that you see, we'll just reuse the same technology. And I've talked a bit already about some of the archive storage systems. The other thing that I've shown on my slides is a media asset management, or a MAM system. And let me spend a few moments talking in more detail about that. So an asset, you might use the words asset and content and file somewhat interchangeably. More formally, I'll define an asset, a media asset, as the content plus the usage rights. So that's what makes it an asset, is the contract, the ability to play something out 3 times, the first run and 2 repeats. If you want to play it out again, so another repeat, more money, a new contract is required. That's what I mean by the usage rights. So turning a file content into an asset is the part of the management of that usage rights. And an asset management system will keep track of that sort of thing. produce reports of when each file was played out, what time, how many more times can I play it out, things like that. The content itself, the words that we'll use to describe the components of that are the essence and the metadata. So essence is another way of describing the video and the audio content itself, right? It's the frames of video encoded however, by whatever codec we're using, the audio samples, that's the essence. The metadata is the descriptive information about that content. And really the metadata is the key to automating this whole system. Metadata is used for searching for the assets, from archive or from nearline storage. It's for automated transcoding, automated playout. Those systems need to understand what the content is. What format is it? What's the play time? Sort of simple things like that, all the way up to human readable things like, what's the program title, the series name, episode number, things like that. The key thing about metadata is really that's what enables an effective asset management system. A lot of the things that you want to do with a file rely on the metadata. If you're searching for content in an archive, it's not going to be from just a file name. Searching for a file name, often they're pretty cryptic. It'll be the database attached to the asset management system can find that clip from keywords that you're searching for. A really good example of that would be a news organization, right? If a politician says something and, quick, what did he say 6 months ago? To be able to find that video clip and bring it out of archive, bring it to nearline storage so that you can put together a piece for the evening news, that relies on really good metadata, descriptive metadata being added to that content when it was first brought in and then moved to the archive. So I think a key attribute of asset management systems, when you're talking to those vendors, be how they manage the metadata, how effective, how efficient are they at managing that. The other thing about metadata is it enables a lot of automation in the workflow. So it's not just the human angle for the metadata, it's the automated angle. For a file to have characteristics, what's its format, its play time, its aspect ratio, things like that need to be fed into an automation system. Or, if you think of another word of mezzanine, it's kind of that intermediate level between, the lobby floor and the higher floors. That's sort of the notion here with the mezzanine file. It's an intermediate format. It's typically a compressed format. So we have to, when we take uncompressed video, camera output in SDI, to get it to a mezzanine format, we are compressing it down. But we're compressing it down not all the way to, say, a broadcast format bitrate. If you look at some examples I've got on my slide here of the mezzanine file bit rates, they're in the 1 to 200 megabit per second range. That's 10 times higher than what a over-the-air broadcast HD bitrate is, but it's also 10 times lower than uncompressed SDI, which is 1.5 gigabits per second. The idea here is a mezzanine file codec, and the examples here you can see like Apple's ProRes and Avid use DNX HD, also known as VC3. When those vendors sort of compete of why my codec is better than the others, the idea is you're compressing it down, 10 to 1 from the uncompressed original, but with the same perceptual video quality as the original. That's the goal of those kind of codecs, to make it just as good as uncompressed video, but occupying only 1/10 of the disk space. So a mezzanine file format is optimal for that intermediate working copy. You can do your editing from that, and it's very easy because another attribute is that it's iframe only. So if you don't know what an iframe is, a lot of compression formats have different frame types. An iframe is the entire image, essentially, and then it's only transmitted every now and then. In between, what we do is instead of transmitting the entire frame again, we transmit the differences. And those are called P frames or B frames. So it's the difference from, if you imagine a a news broadcast, someone sitting behind a desk, the difference between one frame and 33 milliseconds earlier, just subtle changes. So some of the compression technologies take advantage of that and just record the little differences. Well, this pixel moved here and this one moved here. So that's how we get the really high compression. That's not so good for editing though. If you want to cut and it turns out it's one of those intermediate frames, the editing software has to reassemble that frame that it's only got the difference information from. A mezzanine file format avoids that problem. Every frame is complete, so we can make an editing point wherever we want, and it's just that much easier without having to reassemble that frame information. Okay, so our mezzanine file format then, say it's lightly compressed. To get it down to one of our broadcast rates, that's where transcoding comes in again. And if we're starting off with a very good visual quality high bit rate, we're not going to suffer from something called generational loss. Right? If you transcode something over and over again from one format to another, if you start off with something that's compressed all the way down and transcode it to something else, you'll get more and more artifacts. So working with a mezzanine file sort of avoids that problem as well. Okay, so talking about, well, let me just back up one. Mezzanine file format sort of introduces me to the next part of the presentation. You'll notice that a common container format here is something called MXF, or the material exchange format. What I'm going to do now is go into more detail on that particular file format. So I'll sort of warn you already, this is the techie part of the presentation. So for some of you, this might be quite cool, actually. So a container then, or a wrapper is the other phrase you might hear referring to a file format. The idea is it's how we contain our video essence, our audio essence, and metadata together into one package. So a lot of times that will be a single file, but it doesn't have to be. Our container can actually be a bundle of multiple files that work together. And I'll describe one example of that a little bit later. But the key thing is that the container or the wrapper includes those three components essentially. And here I've listed some examples of different file formats. A lot of them are optimized for a specific application. So a really good example, MPEG transport stream is a file format that's optimized for playout. It's ready to play. We can basically spool that file to the playout. It's already pre-packetized into the chunks that you see in an MPEG transport stream. Other file formats are optimized around editing, so a different part of the workflow. A transport stream is not very convenient for an editor. So this is where MXF came to be originated. So the material exchange format is what MXF stands for. It was designed by committee, basically. A lot of these other file formats, especially QuickTime, that was Apple's invention. And ASF, or Windows Media, that was Microsoft's invention. And they had different reasons for creating those formats. They're consumer file formats, or in Apple's case, QuickTime was also enabled a lot of professional editing applications, of course with Final Cut. And so, it was an editing type file format. In any case, MXF was designed by SMPTE engineers with broadcast professional video applications in mind. I would say MXF is about, what are we, about 7 years old, I guess, from the original standards as they were published. So in the big scheme of things, it's still relatively new. The most recent set of revisions are from about 2009. Yeah, oh, okay, here we are. 2004 were the original, so I guess that's 8 years. It turns out there's like 30 or 40 SMPTE documents that fully define MXF. It's huge. And maybe that's a byproduct of being designed by committee. Everybody had their input to it. And so MXF collectively has a lot of features. That's both a blessing and a curse, I would say. The blessing is that you can do whatever you want with the right choice of MXF features. The curse is that interoperability is a little bit difficult, and I'll speak to that point a little bit later. I warned you that it's going to start to get a little bit technical. But it helps to understand. You know, I have this part of the presentation. You know, the feedback I'm getting is it's helpful to understand how a file format works inside. You know, you can kind of see where some of the problems can arise and how some of the solutions are solved. So in any case, the MXF level, there's different ways of looking at it. We'll start at the outermost level, and it's a series of partitions. So there's a header and the body, multiple partitions, and the footer. So that's pretty straightforward. The header is lots of metadata, describes what comes in the file. The body partitions are chunks. They may be 1 minute long or 10 minutes long or a few seconds long or whatever, but they're chunks of our video and audio essence along with other metadata and other kind of data tracks. So closed captions, time code, they can be separate tracks in this body partition section as well. And then the footer, in most cases, it's another copy of the header, just to sort of repeat it. But for some applications, it fills in information, metadata information, that we didn't know when the header was being created. So a really good example of that is recording. If you're creating an MXF file, when you write that header partition to disk, you don't know how long the recording is going to be. It's sometime in the future when we press the stop button. So in the header partition, the field that says what the play length is will be kind of left open and blank, and we'll point to the, say we'll fill that in later. When we do press the stop recording button, that's when the footer partition can be written, and we know how many frames have we written. We can fill it in then. So the footer partition sort of fills in the incomplete parts of the header information. Okay, drilling down, the next level of structure in the MXF file is something we call the generic container. The generic container, there's different elements inside it. The system item, so that's where time code, for example, that I mentioned, a data track that's not formally part of the video encoding or the audio encoding. It's a separate data item. We've got our pictures and the sound, our video and audio. Other types of data, so closed captions are a good example of that. For some kinds of codecs, so DV is an example where the video and audio is already interleaved together, doesn't make sense to rip it apart into separate items from an MXF perspective, so they're kept together and stored in something called a compound item. So in any case, all of these items are put together in one of two ways. Right? Remember I said how MXF has lots of options? Well, here's one particular choice. Do you want to frame wrap the content or clip wrap the content? You might see those phrases, frame wrapped and clip wrapped. The idea is frame wrapped content has, you can see I'm mixing it together. I multiplex one frame of video with however many audio tracks I've got corresponding to that frame. Here I've got 4 channels, I guess, of of sound samples here. So each sound element, there's multiple elements in an item, but in any case, this is the key attribute. You see that each group here has the picture, the associated audio, and the associated data, our captions, time code, and so on. So that frame wrapped is good for playout, right? It's sort of a playback device when it's presented with a frame wrapped MXF file, doesn't have to buffer very much, right? It's got the video and the audio together at about the same point in the file, and it can just move from beginning to end. Contrast that with clip wrapped, and here we've got all of our video all together, followed by all of the audio, followed by all of the data. And in fact, this is often stored in separate physical files. So logically it looks like they're concatenated together, but they can actually be stored in different physical files. So it's not just one .mxf file on the disk, there's several. This you may think, well, that's a terrible implementation, because if you wanted to play this out, right, you'd sort of have to, if it was in one file, you'd sort of have to buffer up or seek from here to there to get the associated audio with the video. But clip wrapped is much easier to work with when you're editing the video, right? If you want to make changes to the video here, you might not even have to touch the audio because it's not intermingled with it. It's at a different point of the file, right? So we enable both playback and editing with the two different styles of wrapping.
Are the sound elements in the frame wrapped associated specifically with that frame?
Yeah.
Or are they part of the error correction that enables for them to be spread across a wider range?
Yeah, that's a good question. Typically, it's sort of each group here is sort of a single frame with its associated samples. So if you think of in an SDI frame, you know, an uncompressed, you've got lots of audio samples sort of occupying that ancillary data space. It would be sort of all of those samples associated with that one frame would be packaged together the same way here. Drilling down one more level deeper, you might see this phrase in conjunction with MXF, KLVs. That stands for key length value. And at the very bottom level of the whole MXF structure, everything is a KLV. And the idea is that the K stands for key. And that's 16 bytes of information, so you know, pretty big identifier. But it says, what is the thing that comes next? Is it a frame of video? Is it a timecode value? Is it a string of metadata, you know, the program title or something like that? So everything in the MXF file has a key associated with it. And SMPTE published something, I'll talk about this in the next slide, but it has a universal label. So it's like a well-known dictionary that says this 16-byte value means this. Another 16-byte value means something else. So an MXF decoder then, basically it goes through and it reads the 16 bytes for the key value, looks it up in its dictionary, aha, this is video or whatever. The L field, the length, says how many bytes long is the actual value, and then the V, of course, stands for the value. So we can extract that piece of information, do something with it, and then move on to the next one. So the MXF decoding process is basically going through this sequence of KLVs and figuring out what is my next piece of information, doing something with it. What is the next piece with the key, figure out the length, do something with it. If there's a piece of metadata, for example, that is unknown, a lot of vendors can have their specific metadata values. So vendor A might not know the key value for vendor B's metadata. That's okay, because with this structure, through the L field, we know where the next KLV starts. We can just skip over it. So the idea here is to aid in interoperability. If you don't understand a particular key value, just skip over it and go to the next one. Here's an example of a key. You see, it's 16 bytes long, so it's pretty verbose. But this specific set of 16 bytes refers to the main title. So SMPTE have defined this specific value, meaning it's the title of that clip. And then the length says how many bytes for the value, and then the value itself. So this is the text characters for what I cleverly called program name, you know, uppercase P, R, O, that's the hex bytes for it. The idea then is an MXF playback viewer, or you know, a playback device. As it's parsing the file, it looks at the key, figures out what this is, and then uses the length value to extract that data and does something with it. If it doesn't know what the key is, if there's some, you know, vendor A has a key value that they use and vendor B doesn't understand it, the vendor A product can use the length value to skip to where the next KLV starts. So you can parse an MXF file without necessarily understanding all of the KLV elements in there. Of course, you know, any sort of robust product would obviously know all of the SMPTE standard key values and be able to process them accordingly. But this mechanism allows for the opportunity for some vendor-specific keys in there as well. And that's where you get, you know, the idea of Avid MXF versus somebody else's MXF. There's some...
Have to be available all the time.
Yeah. Yeah. So now we'll sort of step back out a little bit. So in addition to, you know, we've looked at the partitions and containers and KLVs. Another way of looking at an MXF file is the logical view instead of the physical view. And here, we have two concepts, a file package and a material package. A file package says how those pieces are arranged in the file. How many video tracks, audio tracks, data tracks do we have, and where are they? The material package says how it played out. And the distinction is kind of interesting. Normally when you think of a file, you know, again, your PC at home example, you double click on a file and it plays from beginning to end, and you see all the video and you hear all the audio. Well, MXF allows some different constructs. Here I'm showing what's called an edit item, and you notice the file package, or sorry, the material package is a subset of the file package. The idea here is, let's say you know, a news gathering, you record something. When it goes back to the editor, say, okay, well, cut off this bit, cut off that bit, you know, we just want that middle segment or a collection of middle segments. In MXF, you can create that file not by rewriting the entire new file, but changing the material package pointers to say start here and end here. So it's a much simpler file operation. You don't have to create an entirely, you know, write maybe many gigabytes of an entirely new file. You just change a couple of pointers. Where do you start, where do you end? And that can be repeated throughout the file. Right? So that's an editing operation that's enabled by this particular concept in MXF. Here's another example. They called a playlist. So the idea is your file package can be multiple tracks. The material package says, okay, we'll play this one and then do this one afterwards and then do this one. So from a playout perspective, you're gathering bits and pieces from multiple sources. And again, that's enabled in MXF just by changing the pointers in that material package to say, start here with this file, and then when it finishes, start here in this file. So there's a lot of flexibility enabled by this structure. But again, that adds to some complexity. Those different packages are identified by something called the UMID, the Unique Material Identifier. And it's kind of an interesting idea. A UMID, it's a long identifier. It's either 32 or 64 bytes, so that's a lot of bits. The idea is that it is created locally but globally unique. So you're guaranteeing that, you know, if I'm editing a clip and I identify it with a UMID value, that will be unique. Some other editor in the facility or anywhere in the world can be working on an MXF file and creating new content. It will have its own unique UMID. So a UMID is something where the asset management system can use those to locate individual clips and figure out how to stitch them together. So an example of how this is locally created but globally unique, see some of the options here. You can put, you know, altitude, longitude, latitude. Imagine you've got a GPS receiver on your camera. So wherever you're recording it, you know, that's a unique physical space. Encode that, you've got 12 bytes of information. You're guaranteed that that's going to be a unique value for the content that was shot by that camera. All right, so, you know, I've talked about metadata before, kind of bring it back again. I would say that's one of the key attributes of MXF is that it is metadata heavy and by design, right? It was recognized early on in the creation of this new file format for professional video applications that metadata is key. So there's a lot of different values have been identified, and again, they have their own unique key value. It's called a UL, a universal label. And I've got a bunch of examples here. You can see some of them, I guess these are all descriptive metadata values. You know, there's also some structural metadata values. So, you know, where does the file package, or, you know, in the material package, where does the file package begin, things like that. With the descriptive metadata, these are the ones I've listed here are mostly sort of human related. You know, you can see there's rights information, what are the titles, things like that. This is kind of interesting, you know, did the file win an Academy, or the content win an Academy Award? You know, stuff like that can be put in there. So there's a lot of metadata values that can be associated with the file, and that would be up to the, when it was created, you know, the asset management system provides the ability to add that to the file, and then it's perpetually kept and carried along with that file. Okay, just to close then on those packages, MXF defines something called an operational pattern, or an OP. So if you've worked with MXF, you might have seen the phrase OP1A and OP1B and things like that. The OP stands for operational pattern, and what it does is it describes the constraints of our material package and our file package. And there's two dimensions, the item complexity and the package complexity. So those examples I gave before, we have, an edit item was the idea where you could choose a subset of the file package. The playlist item is where they're strung together. This package complexity, this talks about how many different files can the content be pulled from. So with these two dimensions of 3 options each, you end up with 9 possible operational patterns. So they're called OP 1A, 1B, 1C, and 2ABC, and 3ABC. There's actually a 10th one that I'll describe in a few moments called OP Atom. But these operational patterns, collectively define all the different possibilities with MXF. As it turns out, this is not really fully utilized yet. I would say, high 90-something% of MXF implementations are using OP1A, OP1B, or OP Atom, the 10th one that I haven't described yet. OP1A, then, is the simplest way. I'll keep this slide up. It's the way you typically think of a file. It plays from beginning to end. It's self-contained. There is one .mxf file on that disk. OP1B is a little bit different. Basically, you see that the material package references multiple file packages, typically in separate files. So this is a concept that's also present in QuickTime. You might have seen something called a QuickTime reference file, where the .mov actually points to the video and the audio in separate files. In MXF, that concept is stretched even further, because typically each channel of audio is in its own separate file. Closed captions, if they're present, in their own separate file. So the MXF file is actually a bundle of many files, and the OP1B file that glues them all together is actually pretty small. It's usually sort of 20 to 30 kilobytes in size, even though the entire bundle is several gigabytes in size. So that's the difference then. OP1A is our frame-wrapped file ready for playout typically. OP1B, that's where you've got the multiple essence containers. And then this 10th pattern, OP Atom, is kind of like a simplified, oversimplified version of OP1A. It's got the constraint that it includes just a single track of essence. So just the video and nothing else, or just a track of audio and nothing else. OP Atom is very widely used for recording, right? Because you've got each chunk of essence, my video, my audio, is an independent file. It's easy to work with, especially because from recording, the next step is editing, and having your essence in separate independent files makes editing that much easier. You don't have to work with them all mixed together and sort of extract out the piece you need. Now, looking at this, you see there's a lot of possible complexity with MXF. So, by virtue of that complexity, we saw a lot of interoperability problems. And that led to an industry organization called AMWA, or AMWA, the Advanced Media Workflow Organization. This is basically equipment vendors and broadcasters working together that say, okay, let's try to constrain MXF even more. Let's create what we call application specifications. You might have heard of AS02 or AS03 or AS11. I'd say are the 3 that are most commonly used. They're specifications that say, okay, we'll use MXF, but trim it down. We'll specify here are the mandatory elements of metadata that must be in the file. Here are the mandatory, restricted set of choices for a lot of MXF options. So a good example, this one, AS03 for program delivery. It says must be OP1A. You don't have any other choice. Must be either MPEG-2 or H.264 video. Cannot be any other video type. So it's a constrained version of, you know, the allowable options with MXF. You've got 3 choices for the audio, no more, and so on. So there's a lot of other constraints, as I mentioned, about what type of metadata is mandatory, must be there. AS02 is kind of neat, and I've got a whole slide that talks about that. AS02 is intended for editing or versioning applications. And it's an example of what I was talking about a few moments ago about a reference file. The idea here is that we have a mandated directory structure on our disk where this file, the .mxf file at this level of the hierarchy, that's the one that describes the full version of the file, video and audio combined. It's that OP1B file I was describing earlier that's only 20 or 30 whatever kilobytes long. It has pointers to specific files here, the video tracks and the individual audio tracks, that must be in a subfolder named media. So part of the AS02 specification is, you know, that subfolder must be lowercase media. You have no other choice. That makes it easy for vendors to interoperate. They know that that's where the files will be. The name of this subfolder is always called media, and so on. The idea here, and this is quite clever, let's say you're making different versions of the file. Maybe you've got a different audio soundtrack for international distribution. You know, have a dubbed soundtrack. Well, to create that, the video doesn't need to change. We don't need to touch the video essence file to create a new audio set of tracks. We just record the audio tracks, store them in their own files, and we might have a different revision file here that points to the Spanish language dubbed version. This would point to the same video track, but different audio tracks are made for the airline broadcast. You know, their versions, they're usually edited a little bit from the theatrical version. Same sort of thing. Our OP1B file here can point to the video track, but with different pointers of, you know, which part to skip out, you know, the naughty bits that aren't available on the airline viewing. So we can have multiple versions of the file in a much more efficient way of packaging it together than having, you know, 20 different 10 gigabyte files stored on this disk. Each of the components with these different pointer files can reconstruct the different versions of those files. Editing is much easier, right? If we're creating a stereo mix from our original 5.1 mix, just write a new audio track, adjust some of the pointers here, and we're done. We don't even have to touch the video file, nor should we if we're just editing the audio. So that's the editing and versioning application is much more efficient with an AS02 structure. And lastly, they've even made provision for other stuff. So in the cleverly named extra folder, you can have a QC report, so an XML file there. Maybe there's the cover art of the movie, you know, a thumbnail.jpg file. That will all be stored in this bundle. So any file operation, if you were to copy this file from server A to server B, that copy operation must include everything that's sort of shown diagrammatically here. Okay, so let's come back from the detailed level. So hopefully that wasn't too obscure, but I always find it interesting talking about MXF. It sort of shows what can be possible with a file-based video workflow. So I'll conclude my presentation by talking about quality control of file-based video. And what do I mean by quality control? So traditionally that was visual inspection. You would sit down in front of a picture monitor. Maybe you've got a nice surround system in the room so you can hear the audio as well. Hopefully a Tektronix waveform monitor at the side, and you play the file back, and you're taking a look at, you know, any gross video or audio errors that happen to be in that clip, maybe levels that need to be changed, things like that. But really this approach is only effective if you're dealing with small volumes of content, or you know, if it's, say, a feature-length movie, something you're actively working on every day, you know, in post-production. This type of approach is really not appropriate for, let's say you're a video-on-demand operator and you're receiving hundreds of new titles each week and you need to check them to make sure they're okay for play out. You're not going to have QC staff playing back movies and TV programs continuously. That's where we need to automate things. Also, the kinds of errors that can be caught by visual inspection are just sort of the obvious visual and audible things. If there's a problem where the metadata value does not match the actual value, the metadata says it's a 30-minute program and it's really a 1-hour program, those kind of errors are not necessarily going to be caught by a human operator. That's where automation fits in. So with an automated QC system, which is really what I'm trying to sell, we're trying to make it possible for your QC staff to spend their time fixing, the 5% or whatever of the content that needs fixing, not wading through the other 95% just to find the content that needs fixing. The other thing is it's more consistent, it's more repeatable, and it's more thorough. It can catch some of those errors that are not necessarily obvious during playback type QC. A good example of that, if there's a syntax error, a problem in the encoding of the file, maybe the playback viewer you're looking at in the facility is more robust and more forgiving of an encoding error. The set-top box in someone's home maybe is not quite as forgiving and it crashes on that. So you want to catch those kind of errors that are not immediately obvious to the eye. So let me talk about the types of errors then. I've kind of introduced a couple of them. I'll classify them in 3 different types. So first of all, if we have a problem with the source material itself, this could be a level problem with my white level on my camera, or the audio levels are too high. If there's a problem with the baseband video or audio, that can be baked into the file when it's created at ingest time or recording time. There's an opportunity to fix that earlier on, but once it's in the file, we can still detect it afterwards. Ideally, we can want to fix it earlier, but those kind of errors can make their way into the file. The second category is a problem with the encoding. Now, a few years ago, I would say that, especially a complex codec like H.264, there are still bugs in those kind of devices, and depending on the content that you play through it, could trigger some of those bugs, and you end up with a syntax error in the file that can cause a problem on playback. There's less of that these days. There's probably going to be a whole other wave of that happening in the next couple of years as HEVC, right, H.265 encoders are on the way. It's even more complex and products. They're going to be buggy, so we want to be able to check for compliance against those standards. But there's also the possibility for misconfigured encoders. So a human error, you've picked the wrong profile, so the bit rate is too low or something like that, and you end up with compression artifacts showing up in the content because the wrong profile was invoked on the file. Lastly, we can have a file copy or a transfer error, and the best example I can think of that, one of our customers, they had 10,000 movies in a VOD library, so lots and lots of server space, getting new content all the time. They couldn't check all of these files, and so their viewers at home were doing the QC for them. And every now and then they'd have someone call in and say, hey, I paid $3.99 for this video on demand and my movie ended. What was happening was, even though we're using a potentially robust file transfer protocol, something slipped through the cracks and a truncated file was stored on the VOD server. How that was caught with Cerify was these were Cable Labs VOD files, are MPEG transport streams, and there's supposed to be an end of sequence marker at the end of, the end of the MPEG sequence. That wasn't there because the file was truncated. So a syntax error in the file is how that was caught. And that was through the use of what we call an instrumented decoder. So it's different in a test product like Cerify than in a set-top box or a playback viewer. If you think of, if you were an engineer designing a set-top box and you had something received that was non-compliant with the ISO standards for MPEG, what would you want to do? Well, gracefully handle that error, right? You wouldn't crash the set-top box intentionally or give up on it. You'd want to sort of conceal the error as best you can, gracefully recover from it. Well, that's not so good for a test and measurement product, right? We want to be able to report those errors. And so that's the difference between an instrumented decoder and a playback decoder. And in this case, the instrumented decoder found that this end of sequence marker was not present, reported it, and failed that file in the QC check. So of those three types, I'll go into a bit more detail on some of them, just give some examples. So what do I mean by a baseband error? These are, again, errors in the original source that can get encoded into the file. Right, so from a video perspective, do we have any gamut problems? Is our RGB or Luma out of gamut? And here's a clip I've got where, this is exceeding the peak white value. In MPEG, just as in SDI, there's headroom and footroom above, above peak white and below 0% black. You can actually go negative. And there's limits to how much you can do. So here's a frame where we went out of Luma gamut on the white here, and actually I think the black went below as well. Frozen frames or black frames, if there's a stutter during recording and we have a frozen frame or something gets dropped, we have a sequence of black frames, we can detect that by looking at that decoded image raster in memory. Perhaps the video is supposed to be, again, your acceptance criteria for contributions might say must be full frame, so that if there's any letterboxing or pillar boxing to be added, we'll take care of that. The video coming in shouldn't already have the boxes. Can detect that in the decoded image raster. Take a look for repeated black frame or black areas on the left and right or at the top and the bottom. And that might help avoid the postage stamp problem that can happen if it's sort of fully automated. It's got letterbox coming in or pillar box coming in and we letterbox it going out and boom, now it's postage stamped. In the audio domain, the loudness can be measured while it's still in the file. So the same algorithm that you're starting to see for COM Act compliance, where we have to use the ITU BS 1770 loudness measurement on material as it's being played out, there's like our waveform monitor and other products can make that loudness measurement on the SDI signal. It's just math. We can do the same computation in non-real time when it's in a file. Basically look at the audio samples by knowing which is the left, right, the surround channels. There's different weighting applied to the front channels and the rear channels, but that got all summed together into the loudness measurement, can make that loudness measurement while it's in a file, which is good, right? For COM Act compliance, if you can catch the error well before playout and potentially correct that file as well. That correction can also be done in the file domain. Just rewrite the audio samples, the corrected audio samples back out to the file. And again, going back to my AS02 sample, it's really easy if you're in a format like that. You just basically update the audio track. You don't even have to touch the video track because it's in a separate file. The next type of error, so these are, I alluded to some of these earlier, so encoder errors where you have compression artifacts because the bit rate is too low, things like that. Maybe it's a syntax error, there's slice order problems and things like that. You end up with some of these blockiness artifacts. So that can happen on transmission, on playout, and we've got MPEG analysis tools to detect that sort of thing on broadcast playout. But while it's still a file, it might have been encoded with some of those errors as a result of how it was captured or how it was encoded in the first place. So they can be detected and reported on in the file-based domain.
What kind of performance do you get for this kind of
so the detailed syntax checking can take the longest. So I would say it's, instead of twice as fast, maybe it's now twice as slow. So, maybe a 2-hour check for a 1 hour.
doubled,
Yeah.
would that be characteristic, you would say, from experience?
Roughly, yeah.
Okay.
Yeah.
Thank you.
And then the last type of check, and actually this is the fastest. So oftentimes you'll have acceptance criteria for your content. You say it must be, MXF OP1A must have, one video track that's H.264, must have 8 audio tracks that are, PCM encoded. So that's part of the acceptance criteria for content that's coming in. It's very quick to check that sort of thing and report on files that fail that sort of structure. But it can also go a little bit deeper, and we've got the high-level container structure, but we can go a little bit deeper. So for example, count the number of frames that actually, as we play the file from beginning to end through that instrumented codec, we measure the actual play time. So if there's a discrepancy between what the metadata says, it's an hour, 37 minutes, and 24 seconds, well, maybe not, right? If the metadata is incorrect, that measured value can be obtained and compared. Lots of other examples here, the group of picture structure, and if there's a mismatch aspect ratio picture size, you're expecting HD and it's SD, 16 by 9, 4 by 3 mismatch, things like that. They can all be detected as well. All right, so all those checks then, they get put together into a QC report. Now I'll sort of introduce how QC fits into the workflow by starting with what the output is, and that's the QC report. So our QC report is generated on a per file basis or per group of files basis. That report can be saved in the asset management systems database. You could generate a PDF file and email it to an operator, that sort of thing. The key attribute, though, is ideally we want a human readable and a machine readable format for our QC report. What I mean by that is, especially if you've got a fully automated system with an asset management product in place, it's going to be handing a file to the QC system and getting the report back. If the asset management system is then going to make an automated decision on what to do, it needs to be able to read the QC report. And that's where a machine readable format comes in, makes that so much easier to do. And the technology widely used for that is XML. So if you haven't seen XML, here's a very brief snippet of what it looks like. It's a text format that has, descriptive names for the tags and attributes. So here's an example I sort of cobbled together that shows, okay, the loudness value of track ID 482 is minus 28.5. So that string of text could be read by the asset management software and a decision could be made. That's outside of our target loudness range. Do something with a file. Send it for audio correction, for example. XML also has the characteristic that you can format it in a human readable format. So it sort of works both ways. It's machine readable and human readable, which is why it's widely used for QC reports. The next concept I'll introduce is web services. So again, this is a technology that is borrowed from the IT world. Web services, as implied by the name, uses standard web-based protocols for communication between different software systems. What do I mean by web-based protocols? Well, HTTP, right? If we're familiar with web browsing, think of how that works. There's a remote server out there, and from my browser, I send a request and a response comes back. So for web browsing, it's, the request is show me the page, and the response is that page rendered in your browser. But in general, that architecture of sending a request and getting a response is the building block by which we can have software systems talking to each other. So this is not just unique for a QC system like Cerify. Transcoders and asset management systems, they all use these kind of technologies to talk to each other. It's sort of the enabler for a multi-vendor technology in a software environment. So the protocol on top of HTTP is called SOAP, so the Simple Object Access Protocol. It's basically a way of creating a message and sending it in an HTTP request and then getting a response coming back. So it's built on top of our standard web protocols. The other thing I'll just quickly mention, WSDL, it's actually a language that describes the language. It's actually kind of a cool concept, but the idea is you can describe your system's interface, your API, programmatically. So it's sort of a tool to enable web services developers to hook together these systems to each other. I find when I'm talking to some of our new customers about you know, they say, well, what's your API? And I say, it's web services. I get one of two responses. They'll say, oh, okay, I got it. I presume you have the WSDL file? Yep, okay, I got it. They know exactly what the work is to do to integrate those software systems together. Or sometimes they'll get, tell me more. Then I have to explain a bit more. So, putting it all together then, the end result is our web services enabled system. So for integrating with between our asset management system and our QC system, it's this request and response architecture. And it works like this. So we've got our asset management system, the QC system, and it's always a request response protocol. So our first step might be to say, start testing this file. I have an asset, I want it tested against a particular profile. It's you know, it's a AS11 bundle and, you know, MPEG-2 PCM audio, and here's my quality parameters. I want the loudness to be between -22 and -26 LKFS. You know, you basically set a series of parameters that you're checking against for the structure, the video quality, the audio quality. That's all identified by this profile. That launches the testing on the QC system, and the response comes back, yes, I've started that task. Because it's a web services model, we have to keep sending requests. Okay, well, what's your status? I'm processing, I'm 24% complete. A few minutes later, what are you? I'm now 100% complete. Okay, another request, give me the QC report. And the response comes back as XML. So I showed you what the XML looks like in the QC report. That fits naturally into this web services technology for sending a message and getting a response. So this kind of automation is used, I would say, by, you know, larger workflows dealing with lots and lots of files where you have an asset management system in charge of things. The QC system in that environment is sort of sitting to the side, waiting to be handed a file. Okay, test it, all right, and then give the response back. The other approach in sort of smaller workflow implementations is where the QC system would actually be in charge of that workflow. You'd have watch folders on the ingest side, and when a file comes in, the QC system notices, does periodic directory listings, sees, I've got a new file, okay, I'll test it, and then on the output side, the QC system will say, okay, I'll move it to a quarantine folder if it fails, move it to an output folder if it passes. So there's sort of the two approaches for integrating, you know, software applications like this into a file-based workflow. What I've shown here, this is for the larger systems where you typically have a MAM system in charge of that whole process.
So in that scenario you're describing, the latter, it's linear, it's actually the file is going through QC system, so I couldn't do anything else with it. Let's say write it to somewhere else at the same time it's going through QC system.
That depends.
Depends on the architecture.
Yeah, so if I go way, way back. A lot of times these servers allow concurrent reading for multiple applications. And I think I gave this example, I can't remember, I've done this twice today. But MXF, you remember the whole body partition concept, right? You can be writing to a new body partition and reading from an earlier one at the same time. So as long as the file system here supports that operation, you can be QCing something as you're recording at the same time, or concurrent reads. That's sort of all enabled by this technology.
The QC failed, then okay, I didn't wait to get it, let's say, into an archive. I could just say that archive right failed, and just let that go and then run it again. Right. So it only has that double time workflow, let's say, when it failed.
Yep, yep, exactly. Okay, so that was actually my last slide. Oops. No.
So now if it fails, do you have a system where you can send it and fix it, like small little, it can be fixed?
The one
It can be a server that, you know, maybe a service system send fix.
In the most recent version of Cerify, we introduced the first fixing thing, and it's audio loudness correction. So, yep. A lot of our customers are nervous about the idea of an automated fix for some things that they'd rather have a human look at. But loudness seems to be one of those things that people kind of trust, yeah. And so specifically, we've got Dolby's Pro Logic Correction Library, Pro Audio Loudness Correction Library, PALC. It's a software library that they OEM, and we've integrated into Cerify. So it's Dolby's software that does that correction, and then we just rewrite that AS02 bundle, for example, or an MPEG transport stream based with the new audio tracks. But other than that, we just report on it. We won't correct anything other than the loudness with that new option. Okay, I think I might have gone over time a little bit. Okay, so I went a few minutes over. I hope you don't mind, but be happy to answer any other questions here. But I think I guess we're done, right? We're just